Okay, a couple more things we have to talk about with Lewis structures. So when you have different molecular forms of the same element, we have what we call allotropes. So allotropes is a molecular form. They are all made up of the same element, but the way that they are bonded together and the way that they are structured forms a different molecular form. So for example, if you think about something like carbon, graphite is what is in your pencil. So graphite is mostly carbon. Diamond is also mostly carbon. Those are quite different materials, quite different properties, but they're both mostly made of carbon. Another form of carbon is something called buckyballs. If you haven't seen buckyballs, they're something that looks somewhat similar to soccer balls. It's a C60 molecule. They're named for Buckminster Fullerene. And they're structured, as I said, kind of like a soccer ball. But they have quite different properties, as you might expect from graphite and diamond. Ozone is another example. For oxygen, we have O2, which is the air that we breathe, and then we have O3, which is ozone. So ozone, there's actually an ozone layer in the atmosphere that helps to protect us from some of the UV radiation that comes from the sun. But on the Earth's surface, ozone is actually considered a pollutant. It actually has some health hazards if you breathe in too much of it. So speaking of ozone, if we were to draw the structure for ozone, and it's already drawn here for you on this slide, what you find out is that you end up needing a double bond between two of the oxygens. Well, if we've got all three of these structures here, the two structures here, we've got three oxygen atoms, we could put the double bond between the two oxygen atoms on the left or the two oxygen atoms on the right. And there's really not a right or wrong place to put it. So the question is, well, which one of these should you use? Actually, both of these structures are correct, and we typically put an arrow between them to show that these are resonance structures. They're Lewis structures with the same arrangement of atoms, but just a different arrangement of the bonding electrons. So we just move where the double bond is. In actuality, if you were to calculate bond lengths for ozone, which there are ways of doing that we're not going to get into here, what you find out is that these bonds are exactly the same length. Now, if one of these was a single bond and one of these was a double bond, that should not be true. A double bond should be shorter than a single bond, and we'll go into a little more detail about that later on. So what this suggests is that we actually have something, what we actually end up is something that's more like this. And then we get, so we have something that's kind of halfway in between the character of a single bond and a double bond. And what happens is that these electrons from where we're drawing the double bond are actually delocalized. And they go back and forth between these three oxygens to help stabilize the structure. Another example of a compound like that is benzene. So benzene is an organic compound, meaning it's mostly composed of carbon. In fact, there are so many compounds that contain carbon as a major component that we actually devote an entire branch of chemistry to it called organic chemistry. One of the compounds that we discuss quite frequently in organic chemistry is benzene. So benzene, if you draw the structure out for it, has alternating double and single bonds. Well, there's really no difference between putting the single between putting the single bonds where they are and the double bonds here, here, and here, or here, here, and here. They're the same thing. In fact, what we often do is we draw the single bonds and then we put a circle to indicate that those electrons are delocalized and they travel around the entire atom, which helps to stabilize this structure. So let's take a look at an example and draw a resonance structure here. Or see if we need a resonance structure. So we have SO2. So if we look at the periodic table, sulfur is in group 16 or 6A, so it has 6 valence electrons. Oxygen also has 6 valence electrons, and there are 2 oxygens. So I have a total of 12 coming from the oxygen, 12 electrons coming from the oxygen, and a total of 6 from the sulfur, which gives me a total of 18. So if I draw this, I draw sulfur is further down, so that's going to be the less electronegative atom, which means I'm going to put my oxygens around it. And then I'm going to give everybody their octet. So if I count this up, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, which is too many electrons. So I'm going to take 2 away from one of the oxygens and 2 away from the sulfur. And then I'm going to make a double bond between the oxygen and the sulfur. So now if I count this up, 2, 4, 6, 8, 10, 12, 14, 16, 18, which is how many electrons I was supposed to have. Now I put the double bond on the left, but I could just as easily have drawn it on the right. So now I have if I basically flip this structure, I can put the double bond between the other sulfur and oxygen. And either of these structures would be equally valid. Now, what about when you have a case where there are multiple resonance structures, but they're not quite the same thing? So, for example, if we look back at our SO2, these are really just the same structure I just flipped where the double bond was, but I have oxygens on both sides, so this really comes out to be a structure that's just a mirror image of the other one. But if I look at something like N2O, I could draw this by putting a triple bond between the 2 nitrogens. I could draw this by putting a triple bond between the nitrogen and the oxygen, or I could draw this by putting a double bond between each of the 2 nitrogens and oxygens. So the question is, which one of these is the best structure? Well, the way that we determine that is by calculating the formal charge. So the formal charge is determined by the difference between the number of valence electrons in the free atom and the sum of the lone pair plus half of the bonding electrons in a molecule. So there's actually a formula for this, and the formula tells us to take the number of valence electrons and then subtract the sum of the lone pairs plus half of the valence electrons. So let's test this out for one of the structures. And we're going to do the first structure up here. The one that has the triple bond between the 2 nitrogens. So if I calculate the formal charge on this nitrogen, so nitrogen should have 5 valence electrons according to the periodic table. So I'm going to do 5 minus, and we want the sum of the lone pairs, so there's 2 electrons in the lone pair, plus 1/2 of the bonding electrons. So I have 2, 4, 6 bonding electrons here. So half of 6 is 3. 2 plus 3 is 5. So 5 minus 5 gives me a formal charge of 0. Now if I calculate the formal charge for this middle nitrogen, I have a formal charge of nitrogen should have 5 valence electrons minus, there are no lone pairs on that nitrogen, and I have 2, 4, 6, 8 electrons in the bonding electrons. Half of 8 is 4, 0 plus 4 is 4. So I have 5 minus 4, which is not 0, but 1. And then if I do this for the oxygen, the formal charge on oxygen should have 6 valence electrons, and there are 2, 4, 6 electrons in lone pairs around the oxygen. Minus 1/2, and there are 2 bonding electrons. Half of 2 is 1. 6 plus 1 is 7. So 6 minus 7 gives me a formal charge of -1. So I'm not going to go through and do this for all 3 structures, because it's already been done for you. So if we look at the formal charge for each of these, the question then is, how do we know which one we want? Well, there's a couple things that we're looking for. The first thing that we want is formal charges that are equal to or as close to 0 as we can possibly get them. So ideally, we'd like the formal charge on everything to be 0. If that's not possible, we want formal charges of +1 and -1. We want to avoid having the formal charges get any larger than we absolutely have to have them. And the second thing that we want is, if we have to have a negative formal charge, we want it on the more electronegative element. So if we look at these 3 structures and the formal charges that have been calculated, this last structure that had the triple bond between the nitrogen and the oxygen, this gives us a formal charge of -2 on the first nitrogen and +1 on the nitrogen and the oxygen. So if we compare that to the other 2 structures, both of the other 2 structures give us formal charges of 0, +1, and -1. So we can get closer to 0 than -2. So this structure is out. If we look at the remaining 2 structures, between nitrogen and oxygen, oxygen is further to the right on the periodic table, which means it's the more electronegative element. So these remaining 2 structures, we want the one that has the formal charge on oxygen, not the one that has the formal charge on the nitrogen. The negative formal charge, excuse me. We want the negative formal charge on oxygen, not the negative formal charge on nitrogen. So that makes the structure that has the triple bond between the nitrogens the better structure compared to the other 2. Okay, so a couple of exceptions to the octet rule that we need to talk about. One is sometimes we have atoms that are actually electron deficient. So electron deficient means that they have fewer than 8 electrons. One example of this is BF3. So if I draw the structure for BF3, if I count the electrons that should have up, boron should have 3 electrons because it's in group 3 or 13. So a total of 3. And fluorine has a total of 7. So there's 21 coming from the fluorine and 3 from boron, which is a total of 24. So if we count up the electrons in the structure, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Which is how many we're supposed to have. Except for one small problem, that boron does not have an octet. So the only way we can get an octet on boron is if we were to pull one of these lone pairs around here and form a double bond. Now let's look at why we don't do that. So if you calculate formal charges, which I'm not going to make you do because this has already been done for you, then what you will find is if you put a double bond between any of the boron, between the boron and any of the fluorines, you end up with a formal charge of 0 on 2 of the fluorines, a positive 1 on the fluorine that's double bonded, and a negative 1 on the boron. The structure that only has 6 electrons around boron has a formal charge of 0 on everything. So there's a couple of problems with these structures that are double bonded. One is that we can get one that has a formal charge of 0 on everything. And the other problem is that we are putting a positive formal charge on a very highly electronegative atom. Fluorine does not want a formal charge that is positive. It is our most electronegative element. Boron is not going to want the negative formal charge. In fact, fluorine is so electronegative, you will very, very rarely, if ever, see a fluorine that is double bonded. So it turns out that the better structure is actually the one where boron is electron deficient. There are a couple of other examples of that, things like aluminum chloride and beryllium chloride, but the one that you will see most often is boron. So if you're drawing a structure with boron in it, and you're finding that you don't have enough electrons to go around, remember that boron can be electron deficient. Another exception to the octet rule is the odd electron molecule. So if we take something like nitric oxide, which is NO, nitrogen has 5 valence electrons and oxygen has 6. So that gives us a total of 11 valence electrons. If we put our electrons in and draw a structure for that, what you find is that you don't have enough to give everybody their pairs. We're missing 1 electron on the nitrogen. But if you calculate formal charges for both of these, they both end up with a formal charge of 0. So the structure is fairly reasonable. Everybody has their, well, almost everybody. We've got an octet on oxygen. We've got formal charges of 0. We've got the right number of valence electrons. So the structure is reasonable, except for the fact that we don't have an octet on nitrogen. So this type of molecule where there's an unpaired electron is what we call a free radical. It's an odd electron molecule with an unpaired electron in its formal structure, in its Lewis structure. So free radicals are actually very reactive. Molecules do not like having an unpaired electron. So these are going to go try to find something else to react with and form a product that does not have an unpaired electron in it. The last exception that we're going to talk about is elements that can have an expanded valence shell, which means that they can have more than 8 electrons. So for example, if you look at something like SF6, there are 6 fluorines connected to the sulfur, which means that it's got 12 valence electrons, which violates our octet rule. But there are some elements for which that is possible, but there are very specific conditions under which that can happen. One is that they must have an atomic number greater than 12. So Z is the symbol for atomic number. So if you look at the periodic table, an atomic number greater than 12 means we're talking about something that's at least in the third row. So we can have, at that point, we have D shells in these atoms, so we can fill up some of those D shells and have an expanded octet. So again, we have to have an atomic number greater than 12, and we also have to be bonded to a strongly electronegative element. So things like fluorine, chlorine, iodine. We can have an expanded octet if we have an atomic number that's greater than 12, and we're bonded to an atom that is electronegative, that is highly electronegative. So as I said, we do this by using empty d orbitals to expand the valence shell. So we do this in molecules that have elements like fluorine, oxygen, chlorine, things that are very highly electronegative compared to other elements. And if you were to go through and calculate for more charges, you would find that by using the expanded valence shell, we actually decrease the formal charge on the central atom. Let's take a look at an example here. We have PCl5. So phosphorus is in the same group with nitrogen, so it has 5 valence electrons. Chlorine has 7 valence electrons, and there are 5 of them. So that's a total of 35 valence electrons from the chlorines and 5 from the phosphorus. So that gives us a total of 40. So between phosphorus and chlorine, phosphorus is our less electronegative atom, so we're going to put phosphorus in the center. We have chlorine, and we're going to connect all 5 of the chlorines to phosphorus. So we give all of the chlorines their octets. So that gives us 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons, which is what we were supposed to have. We just have 10 valence electrons on phosphorus. But if we look at the periodic table, phosphorus has an atomic number of 15, so it has an atomic number greater than 12, and it is bonded to chlorine, which is a highly electronegative atom. So it can have its expanded octet. Okay, so this wraps up Lewis structures. We will get a lot more practice with this in class, so I will see you in class.